Somewhere in the darkness, nearly 13 billion light-years away, something is shining that has no right to exist. It is not simply distant, it is not merely old, it is impossible. According to everything we thought we understood about cosmology, about gravity, about how matter slowly gathered itself into the first stars and galaxies after the Big Bang, this object should not be there. Not yet, not so soon, not so massive. And yet the light does not lie. It has traveled across almost the entire history of the universe to reach a golden mirror drifting 1,000,000 miles from Earth, and that mirror has seen it clearly. The James Webb Space Telescope was built to look back in time, to peer through dust, through gas, through the faint afterglow of creation itself. It was designed to answer old questions about how the first structures formed in a universe that began hot, dense, and almost perfectly smooth. But instead of confirming our expectations, it has begun to unravel them. In the earliest chapters of cosmic history, we expected darkness, a long, slow dawn, a gradual emergence of the first small stars, faint and fragile, assembling over hundreds of millions of years into modest galaxies. What Webb is seeing instead is something brighter, larger, more organized. Galaxies that appear too mature for their age. Structures that suggest the universe grew up far faster than our equations predicted. This is not a minor discrepancy. It is not a rounding error in a simulation. If these observations hold, then something fundamental about our model of the cosmos may be incomplete. Perhaps gravity behaves differently in the early universe. Perhaps dark matter is not what we think it is. Perhaps our understanding of cosmic inflation or the timeline of structure formation needs revision. Or perhaps the universe was never as simple as we believed. For decades, the standard cosmological model has been one of science's greatest triumphs. It has explained the expansion of space, the cosmic microwave background, the distribution of galaxies across billions of light years. It has given us a coherent narrative of how chaos became order. But now, as Webb pushes deeper into the infrared and further back toward the beginning, it is uncovering evidence that feels almost defiant. Scientists are not panicking. They are not declaring the end of physics, but they are alarmed, because when the universe refuses to follow its own script, history has shown that something profound is about to change. Tonight, we step into that tension, into the gap between theory and observation, into the moment when certainty begins to crack. And we ask what it truly means when the most powerful telescope ever built finds something impossible. If you value deep, thoughtful explorations of the cosmos, subscribe to The Boring Universe. Like this video to help others discover it, and leave a comment below telling us which part of the country you're watching from. Your voice helps shape this community of curious minds. To understand why Webb's discovery feels so unsettling, we must first understand the framework it appears to challenge. Modern cosmology rests on a model often called Lambda CDM. It is an unassuming name for a remarkably powerful idea. Lambda refers to dark energy, the mysterious force driving the accelerated expansion of the universe. CDM stands for cold dark matter, the invisible substance whose gravity sculpts the large-scale structure of galaxies and clusters. Together, they form the backbone of our current understanding of cosmic evolution. According to this model, the universe began 13.8 billion years ago in an event we call the Big Bang. In its earliest fractions of a second, it underwent a period of rapid inflation, expanding faster than the speed of light and smoothing out irregularities. What remained were tiny fluctuations in density, minuscule variations in how matter and energy were distributed. These fluctuations were the seeds of everything that followed. Over hundreds of millions of years, gravity slowly amplified those seeds. Regions slightly denser than average attracted more matter. Gas fell into invisible halos of dark matter. The first stars ignited. They were likely massive, short-lived, and composed almost entirely of hydrogen and helium. These first stars then exploded, enriching their surroundings with heavier elements. From this gradual process, galaxies formed. The key word in this narrative is gradual. Simulations based on Lambda CDM predict a specific timeline. In the first few 100 million years, the universe was a relatively simple place. Small proto-galaxies formed first. Larger, more complex galaxies emerged later through mergers and accumulation. Structure built upon structure in a hierarchical fashion. Like cities growing from villages, complexity required time. Before Webb, our best glimpse into this early epoch came from the Hubble Space Telescope. Hubble's deep field images revealed faint smudges of light, galaxies seen as they were billions of years ago. But Hubble's capabilities were limited in the infrared range. As the universe expands, light from distant galaxies is stretched to longer, redder wavelengths. The most ancient galaxies emit light that arrives at Earth not in visible wavelengths, but deep in the infrared. Webb was designed precisely for this challenge. With its 6.5-meter gold-coated mirror and highly sensitive infrared instruments, it can detect light from objects formed only a few 100 million years after the Big Bang. It is not merely looking far away. It is looking back in time to the universe's infancy. And almost immediately after it began science operations, Webb started seeing galaxies that appeared unexpectedly bright and unexpectedly massive at redshifts corresponding to less than 500 million years after the Big Bang. In cosmology, redshift is a measure of how much the universe has expanded since light left a distant object. The higher the redshift, the earlier in cosmic history we are observing. At redshifts greater than 10, we are seeing galaxies as they were when the universe was less than 500 million years old. According to standard models, such galaxies should be small, irregular, and relatively faint. Instead, some of the candidates identified by Webb appear comparable in mass to the Milky Way, fully assembled systems containing billions of stars. Systems that, according to simulations, should not have had enough time to form. To appreciate why this is so startling, imagine discovering a fully grown oak tree in a place where you expected to find only seeds. The physics of growth would not be violated in principle, but the timeline would seem absurdly compressed. Either the tree grew far faster than biology allows, or our assumptions about its environment were incomplete. In the cosmic case, the growth mechanism is gravity operating on matter in an expanding universe. The rate at which matter can collapse into stars depends on density, cooling processes, feedback from supernovae, and the behavior of dark matter. All of these factors are encoded in simulations that have been refined for decades. These simulations successfully reproduce much of what we see in the present-day universe, from the distribution of galaxies to the large-scale filamentary structure known as the cosmic web. If Webb's observations are correct, then either early galaxies formed stars with extraordinary efficiency, or the initial density fluctuations were somehow larger than we believed, or dark matter behaves differently under extreme conditions, or the interpretation of the data itself needs revision. Scientists are cautious. Some of the earliest claims about impossibly massive galaxies were later moderated as more precise measurements were made. Photometric redshift estimates can sometimes overstate distances. Dust can affect brightness estimates. Stellar population models can misjudge how much mass is required to produce observed luminosities. There is room for refinement. But even after careful analysis, tension remains. Several studies suggest that the number of bright galaxies at high redshift is higher than predicted. Not marginally higher, but significantly so. The discrepancy is not yet a crisis, but it is persistent enough to demand attention. This is how science advances, not through sudden collapse, but through accumulating friction between expectation and observation. What makes this moment so compelling is not that physics has failed. It is that physics may be incomplete. The standard model of cosmology has passed numerous tests. The cosmic microwave background radiation, measured in exquisite detail by missions such as Planck, matches predictions with astonishing precision. The abundance of light elements aligns with nucleosynthesis models. The expansion rate, though debated in its exact value, broadly supports the framework. And yet, the early universe revealed by Webb seems busier, brighter, and more structurally mature than anticipated. To understand what might be happening, we must dive deeper into the mechanics of early structure formation. In the standard picture, dark matter plays the central role. It does not interact with light, and we have never detected it directly, but its gravitational influence is unmistakable. Galaxies rotate too quickly at their edges to be held together by visible matter alone. Galaxy clusters bend light from background objects in ways that require far more mass than we can see. The large-scale structure of the universe emerges naturally in simulations only when dark matter is included. Cold dark matter, in particular, refers to particles that move slowly compared to the speed of light. Because they are slow, they clump efficiently, forming dense halos that act as gravitational wells. Ordinary matter falls into these wells, cools, and forms stars. If early galaxies are more massive than expected, one possibility is that dark matter halos formed earlier or grew faster than our models suggest. This could imply subtle changes in the properties of dark matter particles, perhaps affecting how they interact or how they cluster on small scales. Another possibility involves star formation efficiency. In the early universe, gas was pristine, composed mostly of hydrogen and helium. The cooling processes that allow gas to collapse into stars depend on radiation and molecular interactions. If these processes were more effective than assumed, stars might have formed at a furious pace, building up stellar mass rapidly. There is also the role of feedback. When massive stars explode as supernovae, they inject energy into surrounding gas, often suppressing further star formation. If early feedback mechanisms were weaker or behaved differently, galaxies might have sustained higher star formation rates for longer periods. Each of these explanations is plausible within the broader framework of physics. None require abandoning general relativity or rewriting the laws of thermodynamics. But each demands recalibration, and recalibration at this scale reshapes our understanding of how quickly order emerged from primordial chaos. The deeper philosophical tension lies in the narrative of cosmic evolution itself. For decades, we have told a story of a slow awakening, a dark age followed by a gentle dawn. The first stars flickering on, gradually illuminating the universe. The process known as reionization. When ultraviolet light from early stars and galaxies reionized hydrogen atoms, making the universe transparent to certain wavelengths. This epoch was thought to span hundreds of millions of years. If galaxies were already abundant and luminous earlier than expected, reionization may have proceeded more rapidly. The timeline compresses, the universe matures faster, and with that compression comes a subtle shift in how we perceive cosmic history. The early universe becomes not a sparse wilderness, but a surprisingly active landscape. It is important to emphasize that Webb has not overturned cosmology. The core pillars remain intact. The Big Bang, cosmic expansion, dark matter, and dark energy are not in question. What is in question is the fine-grained detail of how structure assembled. This is often where revolutions begin, not in the collapse of a theory, but in the refinement of its edges. In the early 20th century, physicists believed classical mechanics could explain nearly everything. It took small anomalies in blackbody radiation and atomic spectra to trigger the development of quantum mechanics. The anomalies were not catastrophic failures. They were precise mismatches between prediction and observation. Webb's findings may represent a similar moment, a mismatch at the edge of our observational frontier. As data accumulates, astronomers are refining measurements using spectroscopy, which allows them to determine redshifts more precisely by analyzing emission and absorption lines. Spectroscopic confirmation strengthens the case that some of these galaxies truly are as distant and as early as initial estimates suggest. The excitement within the scientific community is palpable but disciplined. Papers are published. Results are scrutinized. Alternative explanations are explored. No one declares impossibility lightly, yet the word lingers. Impossible does not mean supernatural. It means inconsistent with current models under reasonable assumptions. And that is precisely what makes this discovery so powerful. It is a reminder that the universe is not obligated to align with our expectations. Our equations are maps, not territory. They are approximations of a reality that may be more intricate than we imagine. The James Webb Space Telescope was conceived to extend our reach into the infrared, to peer through cosmic dust and into the ancient past. It has succeeded beyond expectation. But in doing so, it has exposed the limits of our predictive confidence. We stand at the edge of a new observational era, one where data arrives faster than theory can comfortably adapt, one where the earliest galaxies appear not as faint whispers but as bold declarations. If these early structures truly assembled at such speed, then the universe may have been primed for complexity from the very beginning. The seeds planted by inflation may have carried more potency than we realized. Dark matter may have sculpted the cosmic web with greater efficiency, or hidden variables in our models may be waiting to be uncovered. When the first high redshift galaxy candidates began appearing in the data from the James Webb Space Telescope, the reaction was not disbelief, it was caution. Astronomers have learned through decades of increasingly powerful instruments that the universe often surprises us, but they have also learned that the universe can deceive. A distant galaxy can masquerade as something closer. Dust can redden light in ways that mimic extreme distance. A faint smudge can appear brighter depending on how its light is modeled and interpreted. Extraordinary claims require extraordinary verification, especially when they touch the earliest moments of cosmic history. And yet, as the observations accumulated, a pattern began to emerge. Webb's near-infrared camera, optimized for precisely this task, surveyed deep fields of the sky with unprecedented sensitivity. Within months, it identified multiple galaxy candidates with redshifts greater than 10. Some appeared to lie at redshifts of 12, 13. Even higher, these correspond to a time when the universe was less than 400 million years old. To grasp the magnitude of this claim, consider the timeline. The Big Bang occurs. For roughly 380,000 years, the universe is a hot plasma opaque to light. When electrons and protons combine to form neutral hydrogen, the cosmic microwave background is released. Then follows the so-called cosmic dark ages, a period before the first stars ignite. Gradually, gravity draws matter together, and the first generation of stars forms, illuminating the darkness. In the standard picture, the earliest galaxies begin small. They are irregular, chaotic, dominated by intense but localized star formation. Their total stellar mass builds slowly as mergers and accretion continue over hundreds of millions of years. But some of Webb's galaxy candidates appeared not only bright, but structurally substantial. Their inferred stellar masses, derived from their luminosities and spectral energy distributions, suggested the presence of billions of solar masses worth of stars. This was the first tension. In order to accumulate that much stellar mass so early, star formation would need to proceed at extraordinary rates, close to theoretical maximum efficiencies. Gas would have to cool, collapse, and ignite stars with remarkable speed, converting a large fraction of available baryonic matter into luminous objects in a cosmological blink of an eye. Some researchers propose that these galaxies might host unusually top, heavy initial mass functions, meaning they form disproportionately large, massive stars. Massive stars shine brightly and live briefly, which could inflate luminosity estimates without requiring as much total mass. If true, that would ease the tension. But it would also imply that star formation in the early universe operated under conditions quite different from what we observe locally. Others suggested that active galactic nuclei might be contributing to the brightness. If supermassive black holes were already present and accreting matter at high rates, they could produce intense radiation that mimics stellar light. This possibility raised a second, even more unsettling implication. Supermassive black holes, with masses millions or billions of times that of the Sun, are thought to grow over time through accretion and mergers. Finding evidence of such massive objects less than 500 million years after the Big Bang challenges models of black hole seed formation. How do you grow something so enormous so quickly? There are theoretical pathways. One involves the direct collapse of massive gas clouds into black hole seeds, bypassing the smaller stellar remnant stage. Another involves runaway mergers in dense star clusters. Both mechanisms are under active study. But if Webb is seeing numerous examples of early luminous galaxies potentially powered by massive black holes, then these pathways may need to operate more efficiently and more commonly than previously believed. As spectroscopic follow-up began, some of the most extreme early candidates were revised to slightly lower redshifts. This was expected. Photometric redshift estimation, while powerful, carries uncertainties. Spectroscopy, which identifies specific emission lines such as Lyman alpha or oxygen lines, provides more definitive distance measurements. Yet even after corrections, the overall trend remained. The early universe appeared richer in bright galaxies than simulations predicted. This discrepancy is not merely about brightness, it is statistical. In cosmology, we do not rely on individual objects to overturn models. We rely on populations. The number density of galaxies at a given redshift and luminosity is a measurable quantity. Simulations of Lambda CDM generate predictions for how many galaxies of a certain mass should exist at specific epochs. When observed number densities exceed those predictions significantly, tension arises. Several independent research teams reported that the abundance of bright galaxies at redshifts above 10 was higher than expected. The discrepancy was not subtle. In some mass ranges, observed counts exceeded model predictions by factors of several. There are possible resolutions. One is that stellar population models underestimate how luminous early stars were for a given mass. If early stars were hotter, more metal-poor, and more efficient radiators in the ultraviolet, then galaxies might appear brighter without being more massive. This would reduce the inferred stellar masses and ease the conflict. Another possibility is that dust properties in early galaxies differ from modern assumptions. Dust both absorbs and re-emits light, altering spectral energy distributions. If early dust is less prevalent or behaves differently, our interpretation of brightness and mass could shift. However, even with these adjustments, some tension persists. What makes this situation particularly intriguing is that it echoes earlier hints of discrepancy. Prior to Webb, Observations of high redshift quasars had already revealed supermassive black holes existing when the universe was less than 1 billion years old. These discoveries pushed growth models to their limits. Webb now extends that tension further back in time and across a broader population of objects. This is not a single anomaly. It is a pattern emerging at the frontier of observation. The alarm among scientists is not fear of collapse. It is the recognition that the early universe may have been more efficient at building structure than our models assume. One hypothesis gaining attention involves the role of primordial density fluctuations. The cosmic microwave background provides a snapshot of these fluctuations at 380,000 years after the Big Bang. They are tiny 1 part in 100,000 variations in temperature and density. These fluctuations seed all future structure. If, however, there were slightly more power on small scales than currently inferred, early halos might collapse faster and more frequently. This would lead to earlier star formation and more massive early galaxies. Such a modification would require careful reconciliation with CMB data, but small adjustments within observational uncertainties might be possible. Another avenue of investigation considers alternative dark matter models. Cold dark matter has been remarkably successful on large scales. But on small scales, there have long been debates about discrepancies such as the core cusp problem and the missing satellites problem. If dark matter particles have properties that alter their clustering behavior in the early universe, this could accelerate structure formation. Warm dark matter, self-interacting dark matter, or more exotic candidates each produce subtly different small-scale structures. Most alternative models aim to suppress small-scale structure to address other issues. Ironically, Webb's observations might require enhancing early small-scale collapse rather than suppressing it. There is also the possibility that cosmic variance plays a role. The regions Webb initially observed may not be perfectly representative of the universe at large. Overdense regions can produce more galaxies earlier than average. As Webb surveys larger areas, statistical uncertainties will shrink. Science moves through iteration. New data constrains theory. Theory predicts new signatures. Observations refine or reject those predictions. Yet beneath the technical details lies a profound shift in perspective. For decades, the early universe was conceptualized as fragile. The first stars, known as population stars, were thought to be isolated giants forming in pristine halos. Galaxies grew gradually, assembling piece by piece. Complexity was an emergent property of time. Webb's images suggest that complexity may have emerged with startling speed. The cosmic dawn may have been less a gentle sunrise and more an abrupt ignition. If confirmed, this would influence not only galaxy formation models but also our understanding of reionization. The ultraviolet radiation from early stars and galaxies ionized neutral hydrogen in the intergalactic medium. The timing and duration of reionization are constrained by multiple observations, including the polarization of the cosmic microwave background. If bright galaxies were more numerous earlier than predicted, they could have driven reionization more rapidly. This would require adjustments in modeling the ionizing photon budget of early sources. In parallel, Webb has also begun identifying surprisingly mature chemical signatures in some early galaxies. The presence of heavier elements indicates prior generations of stars lived and died quickly. Metal enrichment is a cumulative process. Detecting significant metallicity at very high redshift implies rapid cycles of star formation and supernova feedback. This accelerates the narrative further. Not only did stars form early, they formed, exploded, and enriched their environments with remarkable efficiency. Scientists are alarmed because the margin for error is shrinking. The earliest epochs are no longer theoretical abstractions. They are observable landscapes populated with real objects whose properties must be reconciled with physics. Importantly, none of this invalidates general relativity or the expanding universe paradigm. The equations governing gravity remain intact. The expansion history measured by supernovae and baryon acoustic oscillations remains robust. The cosmic microwave background still stands as a pillar of precision cosmology. The tension lies in the details of baryonic physics and small-scale structure formation. It is here in the interplay between dark matter halos, gas cooling, star formation efficiency, and feedback processes that the complexity of the universe expresses itself most dramatically. Webb has effectively removed a curtain. Where once there were extrapolations, there are now images. Where once simulations filled the gap, there are now data points. As more spectroscopic confirmations arrive, the community is converging on a sober but electrifying conclusion. The early universe may have been capable of assembling massive, luminous systems far sooner than our baseline models predicted. This does not mean our cosmological model is wrong. It means it may be incomplete at the margins, and history suggests that the margins are where revolutions gestate. In the coming years, Webb will continue to push deeper. It will refine luminosity functions, map early galaxy clustering, and probe the interstellar medium of primordial systems. Each new dataset will either reduce the tension or sharpen it. For now, we find ourselves in a rare moment, a moment when the observable universe is expanding not only in space but in conceptual depth. The galaxies that arrived too soon are not merely distant curiosities. They are messages from a time when the universe was young, dense, and evolving at a pace we are only beginning to appreciate. And in their unexpected brilliance, they remind us that the cosmos still holds the power to surprise even its most careful observers.